Okay, let's have a look here. A student investigated the variation of the fundamental frequency f of a stretched string with its tension T. The following is an extract of the student's account of the experiment. I fixed the length of the string at 40 centimeters. I set a tuning fork to 256 hertz, vibrating, and placed it by the string. I adjusted the tension of the string until resonance occurred. I recorded the tension of the string. I repeated the experiment using different tuning forks. How was the tension measured? That's just using a Newton balance, I think it's called. And then resonance is, the student would have known resonance occurred when it was at its loudest. Is it called a Newton balance or a spring balance? And anyways, that's 6 marks there. Draw a suitable graph. So the relationship here is that F squared is proportional to the tension. Or I think you could say equivalently F is proportional to root the tension. Perhaps we should read ahead to decide which graph would be more useful to us. Draw a suitable graph and then use your graph to estimate the fundamental frequency of the string when it's at 11 newtons. Yeah, okay, so in that case it would seem like this one would be more useful to you. So we'll open up Excel now and have a look at that. Okay, I got Excel open. So now we have to transcribe the data over. So I said I'm going to plot frequency frequency should really be on the x-axis because it is the independent variable, and the T tension is what you measure in response to the change in frequency. That's the dependent variable. That should really be on the y-axis. So it should be, well, the root of it, but x and y that way around. Yeah. Let's transcribe that over. So as I was saying, the frequency is the independent variable. So we'll put that first. And then beside that, we've got root of the tension, and that would be in root newtons unit. So let's just see, the frequency is 256, 288, 320, 341, 384, 480, and 512. Am I still recording? Yes, I am. Okay, and then here, well, let's just copy the numbers first, and then we'll take the roots. Whoops. 2.4, 3.3, 3.9, 4.3, 5.7, 8.5, 9.8. Okay, equals square root square root I'm in trouble typing square root of that number. Okay, there's all the square roots, so I'll just get rid of that. Okay, delete that. Right, so what I've done, I've just made the table that I need to plot. I've got my frequency and then I've got my root of my tension. So I can make the plot. Of course, you would have to use graph paper in the exam. It's called a scatter plot. So what things are missing? What do we need? Well, firstly, we need a title. So let's give it some title of like root tension versus frequency. And then we'll have to add in axis titles. So the axis title here is that's the frequency in hertz, and here that is the tension, root tension. Now I'm not sure how to type the root symbol, so I'll just write root tension in root newtons as the unit. But of course, in the exam, you would use the square root symbol. And we'll have to draw a straight line here, trying to fit as many points as possible. Again, nice thing about using Excel is I can just have Excel do it for me. Okay, there we go. And that's the graph. Now, actually, you're supposed to draw the graph going through the origin, which I guess is a disadvantage of using Excel. So I do recall there being an option to force it through the origin, or I'm thinking of the other software, or so I might have to cheat a little bit for Excel and add 0, 0 in perhaps. So do I have to remake it? Possibly. Oh, can I just sneak this down? There we go. Okay, there we go. Right, and that's the graph now. And does that answer it? Draw a suitable graph to show the relationship between the fundamental frequency of the stretched string and its tension. State this relationship and explain how your graph verifies it. So basically you want to say the graph shows that F is proportional to the root of the tension. And this is because it's a straight line. It passes through the points. The data points. And also importantly, it passes through the origin. Passes through origin. Or as my physics teacher used to say, we had this sentence that we have memorized. It's a straight line through the origin verifies the law. Straight line through the origin verifies the law. He used to write this as shorthand, so he wouldn't have to write the full sentence out every time. So anyways, that's the idea. So I think that answers that graph question. Draw a suitable graph to show the relationship. State this relationship. Use your graph to estimate the fundamental frequency of the string when its tension is 11 newtons. Let's have a look. So we'll have to actually calculate root 11 because we can only work with roots of the tension. So root 11 is 3.3. So if we carefully go across, I think I can add in finer lines, possibly axes, more options. Can I add in? What happens if I change this? No, I don't know. Okay. In your graph paper, you'll have little subdivided boxes, so you could read it off a little bit more neatly and accurately. So 3.3. Yeah, okay. I'll have to extend the graph beyond. So I'll have to copy this over and put it in here. Okay, so again, you'll have a ruler and you can do this neatly, but if I was just to roughly estimate it on the screen, there we go. And then 3.3, again, you'll have smaller boxes here. 1, 2, 3, 4. Okay, so you draw a line going across here. That's terrible. Hits that, and then it'll go down. So, I'm gonna say 550 hertz is what I'm going to pick for that. Okay, and then the last part here is calculate the mass per unit length of the string. So you have this formula. 1 over 2L root T over mu, that's equal to F. Now, if we want to use the graph, we need to figure out what the slope term is. So our graph, remember, was root tension versus the frequency. It's pretty close to having that already. If I do a bit of cross multiplying, I'll have 2L on the top and root mu on the top. 2L root mu times F is equal to root T. Or just to be even clearer about it, root T, which is what I put on the y-axis, is equal to 2L root mu times F, which is what was put on the x-axis. So this is the slope. So the slope of the graph is equal to 2L root mu. So that means mu is the slope of the graph divided by twice the length of the string. That will give you root mu. So, whoops. Dear. I'll have to accidentally. How do I? Undo that? Okay, it doesn't matter because I nearly have the formula here. I was just going to square both sides, so you get mu is equal to this side squared. So I'll just write that down again. Mu is equal to slope over 2L squared. And you can get the slope. You know the formula for slope. It's the rise over the run over 2L squared. Now, I'll go back to my Excel graph. So you just draw a triangle, or we can actually almost see a triangle nicely here, but you're supposed to draw a triangle that includes the data. So like just, draw a triangle trying to include the data points, but don't go too far beyond it and don't pick it too small. So you can measure the rise and then divide it by the run. I don't have to do that because Excel has done it for me already. It's 0.0061, which is good because it'll be very difficult for me to measure it off a computer screen. So 0.0061, 0.0061 over, now I think the question said it was 40 centimeter string, wasn't that right? Yeah, 40 centimeters. So that's 0.8 squared, and we'll just take out our calculator and we'll see what we get here. Okay, so that's going to be 0.0061 divided by 0.8 squared. So it's, let's just check, hang on, let's check the calculation. Now actually I just realized in my graph this Excel calculation is wrong because I cheated a little bit because I had to put in the 0, 0. So I wonder now if I just delete that 0, 0, would it affect it much? Let's see. Oh, how do I go back to, I want to get out of pen mode. Okay, there we go. Right, is that going to affect it much? 0.006. Yeah, okay, that's just a tiny bit different. Let's just get rid of that one there. Okay, 0.006 divided by 0.8 squared. So that will equal 5 point, it's unclear how many significant figures to use in this question. It as I want to use 2, but that's a root, add 1. Okay, we'll just use 3. 5.63 times 10 to the minus 5, and it's as you can see, it's mass per unit length. So it would be kilograms, that's mass, per unit length, per meter, like that. Okay. Let's have a check of the answers now. So, if I got enough battery power, let's see. Just about, let's be quick. So, 3 marks for Newton balance, 3 marks for loudest sound, that's the 6 marks. 6 marks for the points correct, 3 marks for the labels, 3 marks for the points being plotted correctly. Oh, 6 marks for taking the roots, is it? Yeah, and then 3 marks for the straight line, 3 marks about the proportional statement, 3 marks about the straight line through the origin, 6 marks for, I got 550, that's within the plus or minus 10 exception. 3 marks for mentioning the formula, and formula squared correctly or stated implied, and then finding it. Now, I'm not sure what they did here to get 5.86. My answer would be slightly more accurate. You get a more accurate answer if you can use the slope, because that actually uses all the data points. I do wonder if whoever did the answer here, if they just subbed in one value from the graph and just solved it as a maths problem. It actually doesn't say how they arrived at it. It just says formula squared correctly. I didn't actually need to square the formula. Oh no, I did at the very end, didn't I? Yeah. So, yeah, this is the only thing that's a little bit different. Probably due to the slope, maybe, or you know, actually, I don't know. I don't know. And there's no statement for what's an acceptable error here. I kind of feel like, you know, if someone was marking me, they might mark me off here, even though I feel like what I did was the best thing to do. Yeah, I really wish they expanded a bit more in the marking scheme here. I honestly don't know if I would have gotten full marks here. I wonder what you think. Well, that was an interesting question. Let's leave it there and end the video before my battery runs out.